So for math induction, we start with n equal to 1. So when I go 1/3 times 1, 4 times 1 squared minus 1, I'm going to get 1/3 of 4 minus 1, or 3/3. Is that equal to 1 squared, or 1? Yes. So therefore, true for n equal 1. I would write that. Super helpful. There's n equal to 1. Next thing, n equal to k. For n equal to k, you just write everything down. And 2k minus 1 squared equals 1/3 k times 4k squared minus 1. And then you do the n equal to k plus 1. And we're going to write everything the way it was. 1 squared plus 3 squared plus ... plus 2k minus 1 squared plus the next term, which is going to be 2 times k plus 1 minus 1 squared equals, and then we're going to grow this one just a little bit. 1/3 k plus 1, 4 times k plus 1 squared minus 1. So far, so good? All right. So then what I would do with this part is I would replace this with what? This thing. Yeah, that's what I would do. Just replace that. So this is 1/3 k times 4k squared minus 1 plus, let's see, what happened here? Oh, 2k plus 2 minus 1 is 2k plus 1 squared equals 1/3 k plus 1. Yuck. That's 4, let's see, 4k squared plus 8k plus 4 minus 1, right? Plus 4 minus 1 is plus 3. That's what it should look like. Now we get to do this. Are you excited?
Oh, yes.
Okay. Yeah, so we're not going to touch this side, but I am going to touch this side. So it's 1/3 k. Let's see. Let's do. It'll be 1/3 4/3 k cubed minus 1/3 k plus 4k squared plus 4k plus 2. And then this is going to be 4k cubed over 3 minus k over 3 plus 12k squared over 3 plus 12k over 3 plus 6 over 3. And then we're going to do still 4k cubed over 3, and still plus 12k squared over 3. And it'll be plus 11k over 3 plus 6 over 3. And I can factor out a 1 over 3. But, uh-oh, what did we do here? Oh, we have to factor this out. So this is going to be 1/3 times 4k cubed plus 12k squared plus 11k plus 6. And I'm going to take out a k plus 1. So I'm going to go 4, 12, 11, 6. And what's the root here? If I have k plus 1, I do a what? -1. So you drop the 4. This will be -4. This will be 8. This will be -8. This will be 3. And this will be negative. Uh-oh.
Shouldn't that 6 be a 3? Because so the 4k plus 2 above from the first step where you FOIL stuff.
Yeah.
1 else, that last step of FOIL is just 1 times 1.
Oh, there's no. Yeah, that's not 2. So there's 3. Like it. So this is going to be a 3, so now I'm good. 0. So this is interesting. This is going to factor into 1/3 times k plus 1 times 4k squared plus 8k plus 3. What do you notice about that? Perfect. And so you can say, therefore true for n equal to k plus 1. Then you do the big therefore statement. Since true for, what's it true for? N equal to 1, that was the first step, and n equal to k plus 1, any subsequent step, then true for all n greater than or equal to 1 by math induction. So I have this one worked out. 7 to the n plus 2 is divisible by 3. You check n equal to 1. Well, 7 plus 2 is a multiple of 3. 9 is a multiple of 3, so it's true for n equal to 1. Then you just put a k in for n equal to k. This is my substitution. Notice it's a second multiple of 3. Then for n equal to k plus 1, it'll be a third multiple of 3 if you go 7 to the k plus 1 plus 2. And then what I did is 7 to the k plus 1. 7 to the k plus 1 is 7 to the k times 7 to the 1, because you add those exponents. This is a reverse exponent expansion. And then, of course, this 7 to the k has been solved here so that we can make this substitution, m2 times 3 minus 2 times the 7, that's where the 7 came from, plus 2 is equal to m3 times 3, because we're saying it's a multiple of 3. And then multiply that out, you're going to get 7 times m2 times 3 minus 7 times 2 is 14 plus 2. Of course, that's negative 12. You can pull out a 3 out of both of those, leaving 7 m2 minus 4 is a 3 times a multiple of 3. And of course, because both sides have the 3, they're both multiples. So it's true for n equal to 1. And you say, therefore, since true for n equal to 1 and n equal to k plus 1, the, I guess you'd say, expression is true for all n greater than or equal to 1, because we started with 1, by math induction.